Hi, class. All right, so I'm going to make this short video just to give you an example of what it looks like to explain the geology of a unique landscape or of a national park. I know that this is kind of a new concept for all of you, so I wanted to give you this example using Zion. What I want you to keep in mind is that this example video is not designed to be a perfect example. I don't want you to think this is how you have to make your videos. I just want you to maybe use it as you brainstorm ideas of how to present the content relating to your national parks. Once again, I highly encourage each of you to be creative and have fun with this process. As you watch this, think about the parts that you like and that are helpful, and think of the parts that you don't like or the parts that you think I could have done a lot better, and use that as you create your own presentations and videos. Okay, so Zion National Park, it's located in southwestern Utah. Here we see an image taken from a very famous viewpoint within the park called Angel's Landing. What's unique about this viewpoint is it gives you just this wonderful view, both up canyon and down canyon. And I like this image because it showcases, I think, what Zion really is famous for. And it's this deep canyon with these tall and colorful and steep canyon walls on each side. So what I want to talk about today is about this rock unit or rock layer that makes up or composes the canyon walls. It's really what makes Zion tick. So we need to understand how this rock layer got there, and we need to understand some of its unique properties that allows it to contribute to such an amazing landscape. Okay, so first off, all right, I have the title here, Zion Stratigraphy. So stratigraphy is a branch of geology that studies rock layers and how they relate to geologic time. Here we see on the right an image of the stratigraphy of Zion, of the rock layers of Zion. If you were to go to another location anywhere on Earth, you would have a different set of rock layers. These are rock layers that formed in succession in this specific location, which now happens to be Zion National Park. Okay. So what I want to point out is that each of these layers was deposited during a unique time in a unique environment. If we look at these layers, the oldest one is going to be the one at the bottom, in this case, the Kaibab Formation. This layer contains lots of marine fossils in a limestone layer, which we can interpret to have deposited in a shallow sea environment anciently. So that means that where Zion is right now, that used to be under the ocean. Okay. We see successive layers above that with different types of rock. We have the Moenkopi that has some mudstone, ripples. We have the Chinle that has some sandstone and petrified wood. We have the Moenavi with dinosaur tracks in it, and the Kayenta. But what I want to focus on is this layer right here, the Navajo sandstone. This is the layer that really makes Zion tick. When you go to Zion and you see the tall, beautiful, colorful walls that really, when I go there, I think, well, that's why it's a national park. It's from these tall, beautiful, colorful sandstone walls. Those large cliffs are composed entirely of this thick and consistent rock layer called the Navajo sandstone. All right, so let's talk a little bit about how this rock layer, the Navajo sandstone, formed. All right, so the Navajo sandstone was deposited approximately 180 million years ago. It was deposited in a giant sand dune desert setting. And some of you might be thinking, well, how can you tell that it was a sand dune desert? There are a few fossils in it that might indicate the environment a little bit, but overall, the Navajo sandstone is pretty fossil poor. There aren't a lot of fossils in there telling what the environment was like. But the big clue as to what the ancient environment was, if you look at this image, you'll see hopefully a pretty distinctive pattern of diagonal lines. Okay, we see them come in different sets. There's this set at the top and this lower set. So these slanted and subparallel lines Those are called cross-bedding. And cross-bedding, it's a depositional feature. It's a pattern that is a result of sediment, in this case, sand grains, depositing and accumulating over time. Let me show you how this works. All right, so in sand dunes, those of you that have been to sand dunes, you might notice that there is usually within the sand dune, there is one side that is really steep and the other side that is less steep with kind of this apex in between. Well, the reason that sand dunes have this pattern is because it's a pile of sand that's accumulated by wind. And wind, it has a dominant direction over time. So as the wind is blowing, it's picking up grains and it's also depositing grains. So it's eroding grains and it's depositing grains, as we see in this diagram. And what happens is the wind will pick up the grains and it will start to carry it up towards the apex of that sand dune. And then once the wind reaches that apex and those grains reach the apex of that sand dune, suddenly there is a barrier that blocks the wind. And now there's no longer enough energy to carry those sand grains. So the sand grains fall and deposit along the steep slope. So that's what we're seeing in this diagram. We see several steep slopes where sand grains are accumulating. And as these sand grains accumulate, the dune will migrate over time. All right. So if you were to go to a modern sand dune and cut it in half with a backhoe, that sounds like a lot of fun. If you were to take a backhoe, tear through the side of the sand dune, you would see a pattern a lot like the pattern we see in this image. And that would be cross-bed sets within a sand dune, which is why we interpret the Navajo sandstone to be deposited in an ancient sand dune desert. If we were to get in our time machines and get in an airplane, a spaceship maybe, and fly above the Utah region, this is what it would look like. So there's Zion, where that star is. We would see a vast desert of sand that covered the entire state of Utah and also some surrounding areas as well. All right. Okay, so now let's think about how this might relate to the overall landscape of Zion National Park. So Zion, located northeast of St. George. We can see these really prominent, almost rounded cliffs throughout the park. Those cliffs are composed of that Navajo sandstone. Okay. Zion has a couple of forks. If we go up the east fork of Zion, we'll get to this very popular geologic feature that's called Checkerboard Mesa. I want you to think about why it might have that name. As we examine this feature, hopefully you can see a crisscross pattern in it. All right. So the Checkerboard Mesa, we have kind of two sets of distinctive lines that crisscross to create the checkerboard. We have these horizontal to sub-horizontal lines, and then we have these more or less vertical lines, and they crisscross in a number of different places. Well, the horizontal-ish, sub-horizontal, maybe slightly slanted lines, we just talked about that. That is a representation of the cross-bedding. So it's from deposition within a sand dune. So what are these vertical lines? Well, if you were to go to a modern sand dune, what you would notice, if you were to pick up a handful of sand and maybe get a magnifying glass and look at the sand grains, you would notice that the sand grains are almost identical in shape and size. So if you were to go to Zion and look at the Navajo sandstone, put your nose to the rock with a magnifying glass, you would notice the exact same thing. The grains are very similar in size and shape. So when you have a rock body that is composed of grains that are almost identical in size and shape, what that does is that means that these grains are kind of resting on each other with a decent amount of empty space in between because they're being supported by each other, right? If you had a mixture of different sizes, that means you'd probably have smaller sizes within the larger sizes, and there would just be less empty space within it. But since the Navajo sandstone, the grains are almost identical and fairly round in shape and size, you get a lot of this empty space. It's microscopic, but there's a lot of it within the rock. Okay. So we call this porosity. So Checkerboard Mesa, the Navajo sandstone in general, it's very porous, meaning when it rains, water can actually seep down into the rock. It will move inward. Okay. And it has this ability because of great porosity. Okay. Well, I want you to think about what happens now if it is cold and the water freezes. So it rains or you have recent snow melt, water seeps into the rock, and now that water freezes. What's going to happen? Well, it's going to expand. And as it expands, it forces the rock apart and it creates fractures. In this case, we get sets of fractures. Okay. So the current reasoning behind the existence of these vertical lines is that these are fractures created from water seeping in to the porous Navajo sandstone and then expanding and wedging the rock apart. So Checkerboard Mesa is a combination of intersecting lines from freeze-thaw, from water freezing and thawing, and also from these depositional lines from cross-bedding. Okay. All right, so I hope that gives you some insight into what sort of things you can kind of present as you talk about national parks. I do want you to go into detail into the geologic history. Basically, your storytelling. You're trying to tell the story of your parks and how they developed in different stages through time. All right, let me know if you have any questions, and good luck.